If a Markov chain starting in some state x has a positive probability of never making it to some state y, then the expected value of the time it takes to get from x to y will of course be infinite. We've seen several examples now where you can have that expected value be infinite even if the probability of getting from x to y eventually is 1. Our goal in this lecture is to produce a condition under which the expected time to reach any state will be finite. To state this condition, I'll remind you a little bit of notation and prove a small lemma that we'll use. Remember that if we have our transition kernel Q and its associated transition operator capital Q, then for any measurable subset of the state space, QB is the restriction of the transition kernel to B and the sigma field restricted to B, and capital QB is the integral operator associated to QB. In other words, it's this integral here, which is the same as just having Q there. The point is that we're integrating over the set B and not over the whole probability space. This is therefore not a Markov operator. It is a sub-probability kernel operator. Recall also that the hitting time TB of a set B associated to a process with transition kernel Q is the smallest time n at which xn is in B. This is a time which takes values in the natural numbers together with plus infinity. We assign the value TB plus infinity if there is no n for which xn is in B. Now, in order to produce a condition under which the expected value of this hitting time is finite for every x, which therefore implies, of course, that the probability that TB is finite is 1, the following simple lemma is going to be very helpful. If t is any natural number valued random variable, and n is a fixed natural number, then we can estimate from above the expected value of t by n times the sum over natural numbers k of the probability that t is bigger than n times k. This is a version of what we might call the layer cake representation, which will come up in the quick proof right now. In order to see why this is true, we just note that the following quantity, the sum of indicator functions of the sets where t is bigger than nk, can of course be written like this. Now that's just the sum over all k less than t over n of 1. But that sum has to be integers, and so we can characterize the set of all integers that are less than the potential non-integer t over n like this. It's the sum k going from 0 up to the ceiling of t over n minus 1. Of course, that's just a funny way of writing the floor of t over n, the largest integer less than or equal to t over n. But the reason I've written it this way is because this is a sum of 1 over a number of integer terms, and that number, since k starts at 0, is going to be this plus 1, which is the ceiling of t over n. And that is bigger than or equal to t over n. So now we have this estimate. The random variable t over n is less than or equal to this random variable here, and if I now take expected values of both sides, that produces this estimate here after multiplying through by capital N. That brings us to our condition. Now, again, remember, it's possible for a process to be null recurrent, meaning that the probability of reaching any particular state from a starting point x is 1, and yet the expected time it takes to reach it is infinite. The condition we're about to give highlights how that can happen. The problem is that although the probability of eventually reaching y from x may be 1, the actual value of the time it takes to get there can be longer and longer if x and y are farther and farther apart. In order to avoid that summation being potentially infinite, we need to have some sort of uniform control over how long it takes to get from x to y. And so that brings us to our condition. Suppose that there is a uniform n and a uniform delta So there's a uniform over all states of the chain, such that starting at any position x, the probability that the hitting time of the set B is less than or equal to n is positive, and in fact uniformly positive, larger than delta, for any starting point x in B complement. Of course, if x is in B, then this probability is just 1. Under this uniform condition, then the expected value starting in x for any x of the hitting time of B is finite. In fact, not only that, but the supremum over all x's of those expected values will also be finite. Let's prove this. First, for any integer little n, the probability that the hitting time is bigger than that little n can be characterized like this. It's the probability of the event that x0 is not in B, x1 is not in B, and so on down the line to xn being not in B. That is, this is the probability, starting in x, that the vector x0, x1 up to xn is in the n-fold Cartesian product of B complement. Now that is a certain finite dimensional distribution probability for the process, and we know how to compute those for Markov processes. That's going to be computed by integrating the kernel successively over x up to a generic state x1, then x1 up to x2, all the way up to xn over this set. Now we'd also usually have an integral over the starting distribution as well, but in this case the starting distribution is a point mass at x, which is why that integral is already taken account of. So in other words, this is this integral here where we're integrating each one of those over B complement. I'm writing it this way. We can think of it as the integral of the function 1, which means we can write that exactly as this. This is the transition operator restricted to B complement to the nth power applied to 1 as a function of x. So in particular, applying this with little n equal to the assumed uniform capital N there, that operator QB complement to the nth power applied to 1 at x is this probability here, but that's 1 minus the probability that the time to hit B is less than or equal to n, and by the assumption of the proposition, that's less than or equal to 1 minus delta. And because delta is positive, independent of x, this, which we'll call alpha, is a uniform number that is strictly less than 1. In other words, for every x, we get that this function here is less than or equal to alpha. That is, the sup norm of QB complement to the nth power applied to 1 is less than or equal to alpha, which is less than 1. Now we're going to use that lemma from the first slide to help us here. In that lemma, we showed that the quantity we're interested in estimating, the expected value of the hitting time of B starting in x, can be estimated from above like this for any particular n, and so in particular using this uniform n that we posit exists. Well, we've just done a calculation to write what this probability is, at least in the case for n, but we just have to substitute kn for n here, and we get that this is equal to n times the sum over little k of QB complement to the power kn applied to the constant function 1 at x. But from what we just showed over here, notice that QB complement to the kn applied to 1 at x, well, we can write that as QB complement to the n, all to the kth power applied to 1. And let's write it to the k minus first power with one more iteration of QB to the n applied to 1. But this function here that we're applying this bigger operator to, that function has sup norm less than or equal to alpha. And we know that these operators, although they're not probability kernels, they're subprobability kernels, are still monotone. And so since this is less than or equal to the constant alpha, this applied to this will be less than or equal to this applied to the constant alpha. Now we can pull that constant alpha out. And this is n times k minus 1 applied to the constant function 1 at x. And now we can do induction on this procedure and conclude that the sup norm of this original guy, qb complement to the kn, is less than or equal to alpha to the k for every k. Well, that means that this has sup norm less than or equal to alpha to the k, and so for every x, this quantity here in absolute value is less than or equal to n times the sum over k of alpha to the k. Alpha is strictly less than 1, so that sum is finite. And so that shows what we wanted to show. The supremum over all x of this expected value is actually finite. To paraphrase what we've just proved, the point is that if there is a positive probability path from any point x into b, then the expected value, starting at x, of the hitting time of b is finite. Except, not quite. In fact, this is explicitly violated by random walks, as we saw. What we need is that there is a uniform over x positive probability, not depending on x, path with a uniform number of steps, n, again, independent of x, into b. If we have that kind of uniformity, then the expected value starting in x of the hitting time of b will be finite for all x, and in fact, its supremum over x will be finite. Now that's a tall order for most stochastic processes on an infinite state space, but a place where it often comes up and is satisfied is finite state Markov chains. And here's a typical kind of example where it can fail. Suppose that our state space decomposes into two pieces, S1 and S2, disjoint from each other, such that starting in S2, we just can't reach S1. That is, there are no paths from S2 into S1 with positive probability. If you start in S1, you may wiggle around in S1 and you could get into S2, but once you get there, there's just no way to get back into S1. That is, for every x in S2 and every y in S1, q of xy is equal to 0. Well, if that's true, then it doesn't matter how many times we iterate it. The nth power of this matrix will also be 0 for any such states. And therefore, if x is in S2, the hitting time of S1 starting in x will always be infinite. And therefore, the expected value will also be infinite. This is an obstruction to having finite expected value. But in some sense, at least for finite state chains, it turns out to be the only obstruction. A Markov chain is called irreducible if, for any pair of states x and y, there is some finite n, so that the xy entry of the nth power of the transition matrix is positive. That condition is violated by this example. What it means is that there will be some potentially very long path from any state to any other state. And with that condition, we will find that any finite state irreducible Markov chain will have finite expected hitting time of any state starting in any other state. To be clear, this TJ here means the hitting time of the set, which is the singleton J. So let's prove this. We're going to use the proposition that we just proved with a uniformity condition that we'll show is satisfied here. So if we fix any state J in the state space, by assumption, for each I in S, we can find some n that might depend on I and J, such that the nth power of the transition matrix from I to J is strictly positive. Well, just to belabor the point about what this means, of course, this matrix product is the sum over all intermediate states I1, I2, up to In minus 1 of qi up to I1, qi1 up to I2, qin minus 1 up to j. And that is, by our formulas for the finite dimensional distributions of Markov chains, exactly equal to the probability that xn, for this n here, is in state j, given that it started in state I. So again, that's what this condition for irreducibility means. It means that there is a positive probability that you can follow some chain of states to get from I to j, for any I and j. Since this is a finite chain, we also get our uniformity for free if we simply define capital N to be the maximum over all I and j of nij. That's going to be finite since there are only finitely many states. Similarly, if we define this number here to be delta ij, that's strictly positive for all I and j, and we can define delta to be the minimum over I and j of delta ij, which will still be strictly positive because there's only finitely many states in that minimum. Now, with those things in hand, note that the event that xn is in state j is contained in the event that the hitting time of j is less than or equal to n. This says that you get to j by time n. And since capital N is bigger than or equal to whatever little n you come up with for a particular I and j, that event is contained in the event that the hitting time of j is less than or equal to capital N. And therefore, the probability starting in I of this event is greater than or equal to the probability starting in I of this event, which is equal to delta ij, which is greater than or equal to the minimum, delta, which is strictly positive. And so we satisfy the uniformity conditions that we proved in the previous proposition, which shows that this is finite for all I and j. So it's finite, but can we say anything meaningful about its actual size? Can we compute it? Well, in the next lecture, we're going to see some tools for finite state irreducible chains that will allow us to always compute these quantities exactly using basic linear algebra. In order to do that, I want to introduce a slightly different variation on hitting times right now, return times. Suppose we start a Markov chain in some state x. Will it ever return to x? This is a slightly different question than about hitting times, because of course, if you start in state x, the hitting time of the set x is always 0. So we have to modify our definition of hitting time a little bit. Given a Markov chain on a state space S, for each state j in S, the passage time of j, which we'll denote tau j, is the smallest strictly positive integer n for which xn is equal to j. Now, if we start in a state I that is not equal to j, then the hitting time of j will for sure be greater than or equal to 1. And so in that case, this passage time is the same as the hitting time that we've been working with. But that's no longer true if you're talking about the passage time to the state I starting in state I. That has to be a time greater than or equal to 1, whereas the hitting time will just be 0. So we give that a name. On the event that the initial state is I, the passage time tau I is called the return time to I. These return times are going to feature prominently in the next lecture, and so I'd just like to conclude now by noting that it's a fairly easy argument to see that if all of the hitting times are finite, then all of the passage times will be finite as well. So that is to say, if the expected hitting time of state j starting in state I is finite and in fact uniformly finite over all states I and j, such as in the case of an irreducible finite state Markov chain, then the largest return time is also finite and in fact is no bigger than 1 larger than this supremum over here. Let's see why that's true. The expected return time of our chain to state I, starting in state I, well, let's just do first step analysis. This is, of course, a nice measurable function of the path. And so that's equal to the sum over all states j of qij times the expected value starting in state j of the passage time tau I of the chain starting at I and then continuing with x as before. Now let's break up this sum into two pieces. When j is equal to I, this is qii times the expected value starting in I of the passage time of I of the chain ix. And then we have all of the states j not equal to I of the same. Now in this first term, we're conditioning on starting at state I. That is, x0 is I. And so regardless of what we have here, this tau I will be 1 since we're in state I at the first step of x. Whereas over here, we're starting x in state j with j not equal to I. And so what that means is that this initial I here just lengthens the path by exactly 1. So on the event in this expectation, this tau I of ix is equal to tau I of x plus 1. Now if we combine those and take out the plus 1 here, that plus 1 times the q of ij's combines with this q of ii to get the sum over all j of qij, which is of course 1. And the remaining terms are the sum j not equal to I, qij, expected value starting in j of the passage time tau I of the original chain from there. Of course, in all of those terms, j is not equal to I, and so here the passage time is the same as the hitting time. Our assumption in this proposition is that those are all uniformly bounded by h, and so this sum here is less than or equal to 1 plus h times the sum j not equal to I of qij. And that sum is less than or equal to the sum over all j of qij, which is just 1, so that gives us less than or equal to 1 plus h as desired. This might seem like a strong condition, and in fact it is stronger than necessary in order to get the result that we want here, but since we're primarily interested in the sequel and applying this to irreducible finite state chains, there's no loss of generality in making this assumption. Next time, we'll see how return times play a key role in actually computing the expected values of all hitting times, and on the way, discuss invariant or stationary distributions of Markov chains.